Our objective in 7.2 is to find the volume of solids generated by revolving a region about a line using the disk and washer method. Before we get into too much about integrals and the methods and things like that, let's review what is volume. We know formulas for certain solids that are of regular shape, such as a rectangular prism or a cylinder. What is the formula for the volume of a rectangular prism? Well, you probably remember it as length times width times height. What does that mean in this picture, and why is it length times width times height? Well, if I take one slice of this rectangular prism, that slice, if I look at it from the end, or if I just slice into it, that's a rectangle. So looking at that rectangle head on, the area of that rectangle is length times width. The area is length times width. The height is that third dimension. That's the third dimension that we're multiplying that area by. So we've got the length times width, the area of one slice of that rectangular prism times the height. Basically taking all of those slices and putting them next to each other, adding them up, that many slices of rectangles. How about in a cylinder? What's the formula for volume of a cylinder? Well, instead of giving the formula, let's do it the other way this time. Let's look at a slice of this cylinder. So if I just slice into it, notice the base or the top of it is what type of shape? It's a circle. Okay, so let's start with what we started with up there. What's the area of that circle? Well, if we call the radius r, the area is known as pi r squared. So we have pi r squared is the area of one of these circles. If we multiply by the third dimension, well, that's the height. So we have pi r squared, the area of one of the slices, pi r squared, the area of one of the slices, times the height. So just like we did for the rectangular prism, we've got the area of one slice, one of the cross sections, times the height, the third dimension. That's how we're going to look at volume even of irregular objects. So what does that mean? What kind of problem is it that we're going to be given when it says it's not a regular shape? Well, let's take a look at the first example that I've given to you on your paper. Let's sketch out what this is describing and see what the picture tells us. Find the volume of the solid formed by revolving the region bounded by the curves y equals x squared, x equals 2, and y equals 0 about the x-axis. So let's first make a sketch of this region that we are described. So I have my parabola, vertex at 0, 0, and I go over 1 and up 1 and over 2 and up 4. So I can also see the other half of it looking like that on that side. Now I'm not too worried about graphing the left half because of the other boundaries that I'm given. I'm also given x equals 2, so that's the vertical line right here, x equals 2. And I'm also given the line y equals 0. That's this horizontal line right here, y equals 0. So when it says revolving the region described is what I'm going to shade, and it's the part that's touching all of the curves listed. So the parabola is being touched, the vertical line x equals 2 being touched, and the horizontal line y equals 0 is being touched. This is the region that I'm going to revolve. So you're going to have to use some imagination here because we are trying to draw a three-dimensional figure. We're trying to draw a solid for which we're going to find the volume on a flat two-dimensional piece of paper. I always like to, after drawing my region, figure out where is the axis of rotation. So it says about the x-axis. I like to draw that in a bold, bright color and show with a little swirly that that's what I'm going around. I'm going to revolve the region around that line. So if I'm going to just draw it two-dimensionally, imagine revolving that. In fact, I'm going to help you a little bit in your imagination process and show you this picture. Here's a graph of y equals x squared. I've graphed this parabola. The axis of revolution is the x-axis, y equals 0, and I've sectioned off the region from the origin up to x equals 2. So this is the same shaded region that you've just drawn on your paper, and now I'm going to revolve around the x-axis. So can you now get a better picture in your head of what this solid looks like? It's not cylindrical. It's not a rectangular prism. In fact, it doesn't really have a name of the regular solids that you've studied in the past. Let's go back and draw that on your paper. How do I draw that on my paper? Well, I know that when it revolved, I saw a reflection down here if I were to take a picture of it two-dimensionally. So I'm going to look and see 1, 2, 3, 4 points above that axis of rotation is where I have an intersection point. So 1, 2, 3, 4 points below will be a reflection of that. Over 1 and up 1 is a point, so over 1 and down 1 is a point. So I'm going to draw. And if you're just doing this with a regular pencil and not color pencils, you may want to just draw this reflection lightly because it's important that you still remember where those curves originated. Now I lightly shade the reflection so I remember that this is just the reflection. It's not the curve that I started with. It's not the region that I started with. And I know that I'm revolving around that. Now if you want to try to make it more three-dimensional like this picture that we see here, you can certainly go all intricate in the picture, but I'm of the belief that a more simple picture is easier. Now remember back to when we said what is volume. We said it's the area of a slice of that solid times the height of the solid. Well, if I take a look at this picture and I slice into this picture, well, actually, let's take a step back. I've sliced each of these solids differently. How have I sliced them? Well, in relation to the height, in this one, the height was going front to back of the picture. I sliced perpendicular to that height. In the cylinder, the height was going up and down. To get my circle, I sliced perpendicular to the height. That's what we want to think when we're talking about the slice or the cross section. I'm going to use those words interchangeably because to me they mean the same thing. So going back to our picture here, if the axis of rotation is horizontal, I am going to slice into this vertically. So I am going to slice perpendicular to that axis of rotation. Now, not really knowing two-dimensionally what that represents, let's go back to the three-dimensional picture. So think about how this object is made. It's revolving around an axis. So it's circular, such that when I slice into it, can you tell that this slice is going to be circular? It's a circle, or we like to call it a disc. Notice that the disc, if I move it to the right to show the slices farther to the right, it gets bigger. If I move it to the left, it gets smaller because the disk is dependent upon where that function is. Now, let's go back to the fact that this is a disk. This is a slice of, or a cross-section of the solid. And remember that volume is simply the area of a cross-section, or slice for short, times the height, or times the third dimension. Well, if I'm slicing it vertically and I'm getting a circle, what's the area of a circle? Pi r squared, the area of that circle. The height, well, the height is going this way because I have circle next to circle next to circle next to circle next to circle to create that solid. So the height is going this way along the axis of rotation. So I'm multiplying by how many these are in the respect to the x direction. So we can call that the change in x. Well, if you start to see what's happening, that change in x, I'm adding up all of those changes in x's that are each of those slices, and adding them up is the sum. So let's summarize what we're doing here. In the disk method, we are adding up all of the slices. If each slice is a circle or a disk, and the area of a circle is pi r squared, and the volume of a solid is the area of a slice of the solid times the height, or the third dimension. Here is the area of one of those slices, the area of the circle, times the third dimension. Or another way to think of it is the sum of all of those circles. Remember that the integral represents the sum. So the sum of all of the disks, or all of the disks' areas. So going back to our problem, I want to visualize that one of these slices is a disk. So I'm going to remind myself that volume is the area of the slice times the height, or easier to see it as integral of the area. In fact, let's write this down because we're going to be using this all the time that we're doing volume. Volume is the integral of the area of the slice. Integral of the area gives us volume. Volume is the integral of the area. Make sure you get that written down and maybe highlighted. That's pretty important. So looking back at our picture, we remember that volume is the integral of the area, and it's the area of this circular disk. So I know that I want to say it's the integral of pi r squared. Well, here's the next thing. Oh, and our disks are moving in the x direction, so it's with respect to x. Right? Disks are moving in the x direction. We pile them from here to here to here to here. Or you can think of, if we go around something that is like the x-axis, then it's with respect to x. Now we need to figure out, well, how do I know what the radius is? So back to our visual here. In fact, back to the visual where I wrote on. Ooh, that's not looking pretty. Let's try to fix that. There, we see that a little bit better. So again, this radius is from our axis of rotation up to the original curve, because down here is just a reflection. So here the length of the radius is wherever the function hits, f of x. So our radius, we could say, is f of x. I want to write on this again. Can we do that? Yes, we can. So I would say that the radius is f of x, the function's length. If I move this disk to the right, it gets longer because the function goes up. If I move it to the left, it gets shorter because the function goes down. It's all dependent upon where the function is. Now, be careful, because if I move that axis of rotation that is at the x-axis, can I move that? Notice how my disk gets longer when I move it this way, because it's not just now where f of x is, it's this entire length right here, the f of x length plus an additional amount that we've moved. A better way to think of it is if I'm measuring a length that's going up and down. Remember how we measured that in area? If I'm measuring a length that goes up and down, I'm measuring the top minus the bottom, the high values minus the low values. So it's f of x minus wherever it hits on the bottom. Now if I move my axis of rotation back to the x-axis, it's f of x minus y equals 0. So it's the function value, in this case, minus 0. Let's go back to the problem that we started working on here. My radius goes from the axis of rotation, I always start it there, to the original curve, so perpendicular to the axis of rotation. So make yourself a note. The radius is the length from the axis of rotation to the original curve. Also make a note, it's perpendicular to the axis of rotation. So we're drawing from our axis of rotation up to the original curve. So our radius is going up and down. Maybe you can see this better if I make it a bright color. Our radius is going up and down. So how do we write down what our radius is? Well, if it's going up and down, we measure from the high numbers minus the low numbers, or in this case, top minus bottom. On the top is the function that is curvy, or the parabola. So x squared. On the bottom is y equals 0. So again, maybe we label this a little bit better and say on the top is y equals x squared. On the bottom is at the line y equals 0. So if I'm going up and down, I'm looking at y values. Y values go up and down. So the top is x squared, the bottom is 0, or just x squared to simplify it. Once I know my radius, I put that into my volume. Volume is the integral of the area, so the integral of pi radius squared with respect to x. So pi, radius is x squared, squared, and with respect to x. Now remember that pi is just a constant, so a lot of times you'll see the volume equation, the volume integral, with the pi factored out and the radius squared left on the inside. Now we just need our limits of integration. So if we're working with x's, we want to ask ourselves, what's the lowest value of x in the region? Here, 0. What's the highest value of x in the region? Here, 2. So there we have our integral, and whether you prefer to solve it by hand or solve it in your calculator, remember exact answers or to at least 3 decimal places. Let's go review the steps that we did for the volume. This is going to be with respect to x when I have a horizontal axis of rotation. The region that I'm revolving, let's call it f of x. I'm going to shade that region first, and then I'm going to show, after I show the reflection, how the radius goes from the axis of rotation to the original curve. So I show that reflection, I lightly shade the reflection, and I draw in my radius from the axis of rotation to the original curve. That's my radius. I label my radius in this situation top minus bottom. Then I can go ahead and plug it in to the pi r squared into my integral. Now, you're also going to have situations where you're revolving a function of y around a vertical axis. What does that look like? Let's draw that scenario. Here's a vertical axis. We'll be revolving our region around that. Let's draw a function this time that we'll call g of y. We will say, oh, and I should have labeled up here the x value a to the x value b because that was in our integral. So we'll label here the y values c and d. So from the y value c to the y value d, we will section off that region that we want to rotate. There it is, shaded nicely. Rotating it around our axis of revolution gives us a reflection. We sketch lightly the reflection so that we remember that our radius is created by going from the axis of rotation to the original curve and perpendicular to the axis of rotation. There is our radius. Let's call it r. How do we measure r in this scenario? Well, if r is going right and left, we measure from big numbers on the right minus little numbers on the left. Because our disks are traveling up and down in the y direction, we are going to measure this with respect to y. So our radius will be in terms of y. So we'll say dy as a reminder. Up here, with respect to x. So we'll say dx as a reminder. So here's our two scenarios: a horizontal axis of rotation with respect to x, a vertical axis of rotation with respect to y.